Welcome to this problem walkthrough on LeetCode number 272, closest binary search tree value 2. In this problem, we explore how to efficiently find the k values in a binary search tree, BST, that are closest to a given target value. It's a great problem for practicing BST traversal techniques and understanding balanced data structures. Let's dive in. In this problem, you are tasked with finding the k values in a binary search tree, or BST, that are closest to a given target value. These values should then be returned as a list, sorted in ascending order. The input consists of three components: the root of the BST, which is the starting point of the tree, the target, a floating point number that represents the value we are comparing against, and k, an integer that specifies how many of the closest values we need to find. The constraints ensure that k is always at least 1 and does not exceed the total number of nodes in the tree. The output is a sorted list of integers containing the k closest values to the target. To better understand the problem, let's look at an example. Here, the input consists of a BST with the structure shown, a target value of 3.714286, and k equals 2. The two closest values to the target are determined based on their absolute differences from the target. For the value 3, the difference is 0.714286, and for 4, the difference is 0.285714. Since these are the two smallest differences, the closest values are 3 and 4. The result is returned as 3, 4, sorted in ascending order. Here's another example. In this case, the BST consists of a single node with the value 1. The target value is 0.0, and k is 1. Since there is only one node in the tree, the closest value to the target is the value of this node, which is 1. The output is simply a list containing this value, 1. Even when the tree has only one node, the problem can still be solved using the same principles. Finally, in this third example, the BST is shown with a more complex structure, and the target value is 2.5. We are asked to find the three closest values, so k equals 3. The closest values are determined again by their absolute differences from the target. Here, the values 2 and 3 both have a difference of 0.5, while the value 4 has a difference of 1.5. These three values are the closest to the target, and when sorted in ascending order, the result is 2, 3, 4. Additionally, the problem specifies a few edge cases to consider, such as when the tree has only one node, when the target lies outside the range of the tree's values, or when k equals the total number of nodes in the tree. These scenarios help clarify how the solution should handle different inputs. When approaching LeetCode problem number 272, closest binary search tree value 2, there are several strategies to consider. The first method is the brute force approach, which involves performing an inner traversal of the BST. This traversal yields the values in sorted order. Once we have this sorted list, we calculate the absolute difference between each value and the target. Then, we sort the values again based on these differences and return the first k values. While this method is straightforward and easy to implement, it relies heavily on sorting, which can be computationally expensive for larger trees. Analyzing the brute force approach further, we can see that its time complexity is O(n) plus n log n. The O(n) comes from the inner traversal, and the O(n) log n comes from sorting the values based on their difference from the target. The space complexity is O(n) due to the storage required for the traversal result. However, this approach has notable drawbacks. It is inefficient for large BSTs because it does not fully utilize the structure of the tree beyond the inner traversal. The reliance on sorting adds significant overhead, making it suboptimal for larger datasets. To address the inefficiencies of the brute force approach, we can use an optimized method called inner traversal with sliding window. The key idea here is to avoid sorting the entire traversal result. Instead, as we perform an inner traversal, we maintain a sliding window of size k to track the k closest values to the target. Using a deque, or double-ended queue, we dynamically add or remove values based on their proximity to the target. This ensures that we only keep the most relevant values throughout the traversal. By focusing on the k closest values during the traversal itself, we eliminate the need for post-processing through sorting. The sliding window approach has several advantages. It is more efficient than the brute force method because it avoids the full sorting step. Instead, it leverages the BST's properties to dynamically track the closest values. However, it still requires a full traversal of the tree, even when the closest values may be concentrated in a specific region. An alternative to this is the two-stack method, which is designed to further optimize the process by simulating a bidirectional traversal. This method uses two stacks to separately track values smaller and larger than the target, allowing us to focus only on the most relevant nodes. The two-stack method works by leveraging the BST structure to efficiently locate and merge the k closest values. First, we use one stack to track predecessors, or values smaller than the target, and a second stack for successors, or values larger than the target. These stacks are populated through partial tree traversal, which avoids visiting unnecessary nodes. Once the stacks are initialized, we merge the two by comparing values from each and selecting the closest ones until we have k results. This approach achieves a time complexity of O log n plus k, where log n comes from stack initialization and k comes from merging. Its space complexity is O log n, due to the stack usage. While this method is efficient, it requires careful implementation to manage the stacks and handle special cases like duplicate values. For this problem, the two-stack method is the most practical choice. It strikes an excellent balance between efficiency and practicality by taking full advantage of the BST structure. Unlike other methods, it avoids unnecessary traversal and minimizes both time and space overhead. Although its implementation is slightly more complex, the performance benefits make it ideal for large trees. Alternatively, the sliding window approach is a good option if simplicity is prioritized over performance, but it does not scale as well due to its reliance on full traversal. The brute force approach is the least efficient and is best used for smaller trees or as a learning exercise. Ultimately, the two-stack method emerges as the optimal solution, with O log n plus k, time complexity, and O log n, space complexity, making it well suited for solving this problem effectively. To solve LeetCode problem number 272, we need to find the k values in a binary search tree, BST, that are closest to a given target. The challenge here lies in efficiently leveraging the structure of the BST to determine the closest values, rather than simply traversing the entire tree and sorting all values by their proximity to the target. The input consists of the root of the BST, an integer k representing how many closest values we want, and a target value as a reference point. The output is a list of k values, sorted by their closeness to the target. Key observations include the BST property, which ensures that all values in the left subtree are less than the current node, and all values in the right subtree are greater. An inner traversal of the tree provides values in sorted order, which is a useful property for addressing this problem. To optimize the process, we can use data structures like a heap or a deque to dynamically track the closest values as we traverse the tree. One efficient approach to solve this problem is to use an optimized inner traversal combined with a sliding window technique. The algorithm begins with an inner traversal of the BST, which processes nodes in sorted order, starting from the leftmost node, then the current node, and finally the right subtree. During this traversal, we maintain a deque of size k to store the closest values encountered so far. Here's how we update the deque dynamically. If the deque is not yet full, we simply add the current value. However, if the deque is already full, we compare the absolute difference between the current node's value and the target with the absolute difference of the farthest value in the deque. If the current value is closer to the target, we remove the farthest value from the deque and add the current value. By the end of the traversal, the deque will hold the k closest values, which can then be returned as a list. In more detail, the inner traversal proceeds recursively. First, the left subtree is traversed. When processing the current node, we check the size of the deque. If it contains fewer than k elements, we append the current node's value directly. If the deque is already full, we compare the current value's proximity to the target with that of the farthest value stored in the deque. If the current value is closer, we remove the farthest value and add the current value to the deque. Finally, the traversal continues to the right subtree. This approach leverages the natural order provided by the inner traversal to maintain the k closest values dynamically. Using a deque is particularly effective because it allows efficient addition and removal from both ends. This is critical for maintaining the sliding window of k closest values while traversing the BST. The algorithm also accounts for edge cases. If k is larger than the total number of nodes in the BST, we simply return all the nodes in the tree. When the target value lies outside the range of the BST, for example, if it's smaller than the smallest value or larger than the largest value, the algorithm naturally clusters the closest values around the boundary. Additionally, if the BST contains duplicate values, those duplicates may appear consecutively in the result if they are equally close to the target. In terms of complexity, the time complexity is O(n), as we visit each node once during the in-order traversal. Maintaining the deque has an O(1) cost per operation, so it doesn't add significant overhead. The space complexity includes the recursion stack, which uses O(h) space, where h is the height of the tree, and the deque, which uses O(k) space. The recursion stack space usage depends on the tree's height, which is O log n, for a balanced tree but can degrade to O(n) for a skew tree. The deque, on the other hand, requires O(k) space to store the k closest values. Now let's look at the pseudocode. We start by initializing a deque to store the k closest values dynamically. The core of the algorithm is the recursive in-order traversal function. This function first processes the left subtree, then evaluates the current node. If the deque has fewer than k elements, we append the current value. Otherwise, we compare the current value's proximity to the target with the farthest value in the deque. If the current value is closer, we remove the farthest value and append the current value. Finally, the function processes the right subtree. After the recursive traversal completes, we simply convert the deque to a list and return it as the result. This ensures that the output contains the k values closest to the target, sorted by their proximity. The combination of the in-order traversal and the sliding window mechanism makes this algorithm both efficient and elegant, leveraging the BST's inherent structure to minimize unnecessary comparisons and memory usage. This concludes the algorithm deep dive for solving the problem using optimized traversal and dynamic data structures. Here, we are implementing the solution to find the k values in a binary search tree that are closest to a given target. We start by importing the deque class from the collections module to maintain a fixed-size collection of the k closest values. Then, we define the closest k values function as a method within the solution class. The function takes three arguments: the root of the BST, the target value, and the integer k, which represents the number of closest values we want to find. Inside this function, we initialize an empty deque called result, which will store the k closest values in sorted order. Next, we define a helper function named in-order_traversal to traverse the tree in order fashion. This traversal ensures that we visit the nodes in sorted order due to the BST property. In the base case of this recursion, if the current node is null, we simply return. Otherwise, we first recursively call in-order_traversal on the left child to explore the left subtree. After exploring the left subtree, we process the current node. If the deque has fewer than k elements, we directly append the current node's value to the deque. However, if the deque already contains k elements, we compare the difference between the current node's value and the target with the difference between the oldest value in the deque and the target. If the current node's value is closer to the target, we remove the oldest value from the deque and add the current value. Otherwise, since the values in the BST are sorted during in-order traversal, we can terminate early without checking further nodes. Finally, we recursively call in-order_traversal on the right child to process the right subtree. After defining the in-order_traversal helper function, we invoke it starting from the root node. This begins the in-order traversal of the tree, ensuring that we examine all nodes in sorted order while maintaining the k closest values in the deque. Once the traversal is complete, the deque contains exactly the k values closest to the target. To match the expected output format, we convert the deque into a list before returning it. This ensures that the result is returned as a standard Python list, making it compatible with the requirements of the problem. This implementation is efficient because it leverages the BST property to optimize the traversal, and the use of a deque ensures that the collection of k closest values is managed in constant time for each insertion and removal. Here, we begin with the definition of the treenode class, which represents each node in our binary search tree. Each node has a value, a left child, and a right child. Then, we define the solution class, where the main method closest k values is implemented. This method takes in the root of the binary search tree, the target value, and the number k, which specifies how many closest values we want to find. Inside the method, we initialize a deque called result to store the k closest values dynamically as we traverse the tree. The core logic of our solution lies within an in-order traversal, performed by a helper method named in-order traversal. This traversal ensures we process the nodes in sorted order, which is key for maintaining the closest values. The result deque is converted to a list before being returned to satisfy the method's return type. The in-order traversal method is designed to recursively navigate the tree while maintaining the k closest values in the result deque. If the current node is null, the method simply returns, ensuring we handle the base case. First, we traverse the left subtree, adhering to the in-order traversal pattern. Then, we process the current node. If the result deque contains fewer than k elements, we add the current node's value directly. Otherwise, we compare the current value's distance to the target with the distance of the farthest value in the deque. If the current value is closer, we remove the farthest value and add the current one. This keeps the deque updated with the closest elements. If the current value is farther, we exit early, as all subsequent values will only be farther due to the properties of in-order traversal. Finally, we traverse the right subtree to complete the process. To understand this problem, let's start with a basic example using a small binary search tree. The tree structure is shown here, and our goal is to find the two values closest to the target, which is 3.714. To achieve this, we'll perform an in-order traversal of the tree, as it naturally visits nodes in ascending order. We initialize an empty deque to store results and begin traversal at the root node, which is 4. The first step is to explore the left subtree, starting with node 2. At node 2, we continue traversing its left child, node 1. Since the deque size is still less than k, we add 1 to the deque, which now contains 1. After visiting node 1, we backtrack to node 2. Here, we add 2 to the deque, making it 1, 2. With the left side of node 2 fully processed, we proceed to its right child, node 3. Adding 3 to the deque results in 1, 2, 3. However, since the deque size exceeds k, we evaluate the oldest value, 1, and remove it because 3 is closer to the target than 1. The deque is now 2, 3. Backtracking further, we return to the root node, 4. At node 4, we add its value to the deque, resulting in 2, 3, 4. Again, the deque size exceeds k, so we compare the distances of the oldest value, 2, and the newest value, 4, to the target. Since 4 is closer, we remove 2 from the deque, leaving 3, 4. Next, we traverse the right child of node 4, which is node 5. Adding 5 to the deque results in 3, 4, 5. However, 5 is farther from the target than the closest values we currently have, so we stop the traversal, as the binary search tree property guarantees that further values will only be farther away. The final output for this example is 3, 4. Now, let's consider an edge case with a tree that contains only a single node. The tree consists of just the root node, 1, and we aim to find the closest value to the target, which is 2. Since k is equal to 1, we only need one value. We initialize the deque as empty and begin the in-order traversal at the root. Visiting the single node, 1, we add it to the deque. With no left or right children to traverse, the traversal ends here. The final output is simply 1. For the final example, we analyze a larger binary search tree with a target value of 9 and k equal to 3. Starting with an empty deque, we perform an in-order traversal. In the left subtree, we visit nodes 4, 5, and 6, adding them sequentially to the deque, which becomes 4, 5, 6. At the root node, 8, we add its value to the deque, resulting in 5, 6, 8. After removing 4 to maintain size k, moving to the right subtree, we visit nodes 9, 10, and 12 sequentially. Adding 9 to the deque gives 6, 8, 9, and adding 10 results in 8, 9, 10 after removing 6. Since the closest values to the target are now determined, the final output for this example is 8, 9, 10. The time complexity of the closest k-values function is influenced by the in-order traversal of the binary search tree. During this traversal, each node in the tree is visited exactly once. If the tree contains n nodes, this results in a time complexity of O(n) in the worst case. While traversing, we perform operations on the deque for each node value. These operations include appending elements, which takes O(1) time, and removing the leftmost element using popleft, which also takes O(1). Since each of these operations is performed at most once per node, the total time spent on deque modifications is O(n). Additionally, the traversal may terminate early if the properties of the BST allow us to skip certain nodes. For example, if a node's value is farther from the target than the farthest value in the deque, we can stop exploring further. This early termination is particularly beneficial for balanced trees and small values of k, though in the worst case, all nodes may still need to be visited. The overall time complexity of the function is O(n) in the worst case, where n is the number of nodes in the tree. Now, let's discuss space complexity. The function utilizes space from two main sources. First, the recursive call stack created during the in-order traversal. If the tree is completely unbalanced, the recursion depth can reach O(n). However, for a balanced tree, the depth is limited to O log n. Second, we have the result deque, which stores up to k elements. Since the deque size is capped at k, this contributes O(k) to the space complexity. Combining these, the worst-case space complexity is O(n) for unbalanced trees due to the call stack. In the best and average cases, for balanced trees, the space complexity is O log n plus k. Here, O log n accounts for the call stack, and O(k) comes from the deque. To better understand the efficiency of the current solution, let's compare it to a naive approach. In the naive approach, all n node values are collected during an in-order traversal, then sorted based on their absolute difference to the target. Finally, the first k values are selected. This approach has a time complexity of O(n) log n, driven by the sorting step, and a space complexity of O(n) to store all node values. The optimized approach, by contrast, avoids the sorting step entirely. Instead, it maintains the k closest values directly during the traversal. This reduces the time complexity to O(n) in the worst case and the space complexity to O log n plus k for balanced trees. Considering different scenarios, the best case performance occurs with balanced trees in small k, where traversal may terminate early, resulting in a time complexity better than O(n), and a space complexity of O log n plus k. On average, balanced trees still lead to O(n) time and O log n plus k space. In the worst case, such as with completely unbalanced trees, all nodes are visited, leading to O(n) time and O(n) space due to the call stack. To mathematically confirm the big O complexities, let's break it down. First, the traversal visits each node exactly once during an in-order traversal, contributing O(n) operations in total. Next, deque operations, such as appending or removing elements, are O(1) each and occur at most once per node. Over n nodes, this also totals O(n). Finally, the call stack depth depends on the tree's height. For an unbalanced tree, the height is O(n), while for a balanced tree, it is O log n. Combining these factors, the time complexity of the function is O(n), and the space complexity is O(n), in the worst case or O log n plus k, for balanced trees. This analysis confirms that the optimized approach is efficient for this problem. When solving the closest binary search tree value 2 problem, there are a few common mistakes that can slow down your solution or cause it to fail. One of the most frequent issues is ignoring the fundamental properties of a binary search tree. A BST isn't just any binary tree, it has a specific structure that lets you navigate efficiently based on comparisons. If you treat it as a regular tree and traverse all nodes, you'll lose this advantage and perform unnecessary computations. Instead, you should prune the search space by moving left when the target is smaller than the current node, and right when it's larger. Another mistake is using an in-order traversal without stopping early. While generating a sorted array of values via a full traversal can technically work, it's inefficient because you may process nodes that aren't needed after finding the k closest values. A better approach is a controlled traversal that uses a priority queue or deque to maintain only the k closest values. Finally, edge cases are often mishandled. For instance, the BST might have very few nodes, the target could be outside the range of the tree's values, or k might be larger than the total number of nodes. To handle these, you should add checks for cases like an empty tree and ensure k is capped at the total node count to avoid out-of-bounds errors. Another common inefficiency is related to priority queues. Some solutions involve pushing all nodes into a max heap or min heap and then extracting the closest k values. While this approach works, it's suboptimal with a time complexity of O n log n. Instead, you can maintain a heap of size k during the traversal, which limits the operations to O n log k. Floating point comparisons are another tricky area. When calculating distances, such as the absolute difference between a node's value and the target, rounding or precision errors can give incorrect results. To avoid this, you should handle absolute differences carefully and ensure consistent precision throughout your comparisons. Beyond specific mistakes, this problem is a great opportunity to highlight transferable skills in an interview setting. First, it showcases the importance of recognizing patterns in tree problems and leveraging BST properties to prune unnecessary branches. Second, you can discuss the spacetime trade-offs between iterative traversal with a deque, which uses the h plus k space, versus recursive traversal with additional storage, which can consume O n space. Interviewers may also test your handling of edge cases, so be ready to discuss scenarios like an empty tree, a single-node tree, or a target far outside the BST range. Finally, this problem often leads to follow-up questions, such as adapting the solution for an unsorted binary tree or handling a stream of target queries. Being proactive in addressing these variations can leave a strong impression. This problem also connects to several related problems, which can help you build a stronger understanding of tree traversal and optimization techniques. For example, LeetCode 270 focuses on finding the single closest value to the target in a BST. LeetCode 230 deals with finding the kth smallest element in a BST, which often involves an inner traversal. LeetCode 378 tackles the kth smallest element in a sorted matrix, where a similar priority queue approach can be applied. Lastly, LeetCode 658 is closely related, as it involves finding the k closest elements in a sorted array. These problems share underlying concepts that can deepen your problem-solving skills. Alternative approaches to solving this problem can also provide valuable insights. One such method is the combination of an inner traversal with a sliding window. This involves generating a sorted list of values through traversal and then using a sliding window to extract the k closest values. While this is relatively simple to implement, it requires O n space and O n time for traversal, making it less efficient for large trees. Another method uses a priority queue, specifically a max heap of size k, to store the k closest values. For each node visited, you compare its distance to the farthest value in the heap. This approach is efficient for large BSTs, with a time complexity of O n log k, but it does require additional space for the heap. A third alternative approach involves using two deques. One deque stores values smaller than the target, while the other stores values larger than the target. After traversing the tree and populating these deques, you can merge them to retrieve the k closest values. This method is optimized for space since it avoids storing unnecessary values, but it requires careful management of deque operations to ensure correctness. Each of these approaches comes with its own trade-offs, and the best choice often depends on the specific constraints and requirements of the problem you're solving. Understanding these alternatives not only helps you tackle variations of this problem but also prepares you for follow-up questions in interviews, where you might be asked to adapt your solution to different scenarios or optimize it further. Great work! We've covered LeetCode number 272, closest binary search tree value 2, and explored efficient solutions using in-order traversal and two-pointer techniques. Remember to practice similar problems to strengthen your understanding of BSTs. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!